Welcome back, students. In section 11.4, we're going to look at calculating probabilities of disjoint and overlapping events. So the first thing we need to discuss is some definitions. So when you consider all the outcomes for either of two events, A or B, you form what is called the union of A and B. So the union of A and B is anything that lies in A or anything that lies in B. So anything that's in any of the shaded region counts as in the union of A and B. The word that we use to represent a union in the English language is often the word or. So if I want events in A or B, I'm looking at anything in A or anything in B. The next thing, when you consider only the outcomes shared by both A and B, we form the intersection of A and B. So if we look at this diagram here, this part here represents the events that are common in both A and B. We call this situation an intersection, and the English word we use often to represent the intersection is the word and, because these are events in A and also in B. Now you'll notice that the intersection is part of the union, but the union includes a lot more stuff than just the intersection. Now you might be asking, do all events have an intersection? Well, no. Sometimes if you have events A and B, they may not overlap at all, and they may have nothing in common. So the union of A and the union of B include nothing in common. This has an empty intersection. Notice there's no overlap between these two events. So we have a little bit of vocab. To find the probability of A or B, we have to consider what outcomes, if any, are in the intersection of A and B. When two events are overlapping, like we have up here, we say they're overlapping if they have one or more outcomes in common, because you need something that's shared in between these two events. So this is called an overlapping, when the two circles overlap. This area of overlap is called the intersection. We say two events are disjoint or mutually exclusive. Those two terms are used kind of interchangeably. They have no outcomes in common. So that's like this picture here, where the circles don't overlap at all, because there's no outcomes in A that are also shared in B. So that gives us kind of two formulas for these two different situations. If A and B are any two events, then the probability of A or B is equal to the probability of A plus the probability of B minus the intersection of the probability of A and B. Now, why do we have to subtract that? Well, the probability of A includes this little overlap, and the probability of B also includes this little overlap. So when we've counted the probabilities, we've actually counted this overlap twice. So by subtracting it out one more time at the end gives us the correct probability there. However, if A and B are disjoint events, like we're seeing here, then the probability of A or B is just the probability of A plus the probability of B. Since there's no overlap, there's no region that we've counted more than once, so there's no reason to do any correction at the end there. Okay, so let's look at some examples here of some situations where we can try this out. So in our first example, we have a card that's randomly selected from a standard deck of 52 cards. Remember, on our deck of cards, we have 4 different suits: hearts, diamonds, spades, and clubs. There's 13 kinds of cards per suit. So you have 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. And you have that for each of the 4 suits. There's 2 colors. There's red cards, so the hearts and diamonds are reds. And there's black cards. The spades and clubs are black. Okay. Now that we've reviewed what the standard deck of cards looks like, we ask, what is the probability of drawing a face card or a 10? So the first thing we need to do is decide whether the outcomes 10 and the outcome face card are these events overlapping. I should call this an event drawing a 10 and the event drawing a face card. Are they overlapping? Is there any cards that are 10s and also face cards? Well, no, right? A face card is a jack, queen, or king. A 10 is the card with a 10 on it. So this is disjoint, because 10s are not also face cards. So the probability of 10 or face card is just going to be the probability of 10 plus the probability of a face card. Okay? So the probability of getting a 10, there's 4 10s in our deck of cards because there's a 10 in each one of the 4 suits. There's a 10 of hearts, a 10 of spades, a 10 of diamonds, and a 10 of clubs. And there's 52 total cards in a standard deck. And then face cards. Well, there's 3 face cards in each suit. There's a jack, queen, king in each of the 4 suits. There's jack, queen, king of hearts, jack, queen, king of clubs, jack, queen, king of diamonds, jack, queen, king of spades. So that's 12 out of 52. So that gives us 16 out of 52, which reduces down to 4 out of 13. Let's look at the next part of this question. It asks, what is the probability of drawing a face card or a spade? So again, this is an or question, just like the previous one was. So we have to deal with whether these are disjoint or overlapping. Here, we should ask ourselves, are there any face cards that are also spades? Yes, right? This is overlapping because, well, I have a jack of spades, a queen of spades, and a king of spades. So the probability of face card or spade is going to be the probability of drawing a face card plus the probability of drawing a spade minus the probability of drawing a face card and, we use that a spade. Okay. Well, the probability of drawing a face card we already did. That was 12 out of 52. Right? We had that right there. The probability of drawing a spade, well, we have 4 suits. Each has the same number of things in them. There's 13 cards in each suit. So if you count 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and ace, there's 13 of those. Minus the probability of face cards and spades. So how many face cards are also spades? Well, there's the jack of spades, the queen of spades, and the king of spades. So there's 3 of those. So that ends up with 22 out of 52, which reduces down to 11 out of 26. Okay. Let's look at another example that involves a situation that isn't cards. So I'll type that up here in a second. So another example here. It says, out of 200 students in a grade, 113 students are either varsity athletes or on the honor roll. There are 74 who are varsity athletes and 51 on the honor roll. What is the probability a randomly selected student is a varsity athlete and on the honor roll? Now, as you read through this quickly, you might say this doesn't make any sense. If there's 113 that are varsity athletes and on the honor roll, and I add up 74 varsity athletes and 51 on the honor roll, that doesn't equal 113. Well, that's okay. That's because there's some students that are both varsity athletes and on the honor roll. So this is clearly a situation, because when I look at that little check, that we have overlapping. So I know the probability of varsity athlete or honor roll is going to equal the probability of varsity athlete plus the probability of honor roll minus the probability of varsity athlete and honor roll. Okay. So we're told we have 113 that are varsity athlete or honor roll out of 200 students. So the probability of varsity athlete or honor roll is 113 out of 200. The probability of a varsity athlete, well, there's 74 of those, again, out of 200 total students. The honor roll, there's 51 of those out of a total of 200 students. And then what we're looking for is this probability that we're a varsity athlete and on the honor roll. Okay. Well, if I take and subtract 74 out of 200 and 51 out of 200, if I subtract those from both sides, I'm going to get 113 out of 200. And then we're going to subtract from both sides 74 out of 200. And 51 out of 200. 51 out of 200. We get -3 out of 50. So I'm going to subtract 74 from both sides and 51 from both sides. That gives me -3 out of 50 equals, don't forget about this guy, negative the probability of B and H. So remember, probabilities have to be a number between 0 and 1. Right now, I have a negative over here, but that's okay because I have a negative in front of my probability. When I divide both sides by -1, I get a positive number here for my positive probability. So I have a reasonable answer. Okay, let's look at one more situation here in this section, and then we'll be done. All right, so the last thing we're going to talk about is something called a complement. So we say the complement of an event A consists of all outcomes that are not in A. We denote the complement of A by the symbol A bar. So notice the bar on top of that. That's the symbol we use for the complement of A. To compute the probability of a complement, the probability of A bar is equal to 1 minus the probability of A. So let's look at an example where we have to use this. So in this example, it says 2 dice are rolled at the same time. Find the probability the sum of the 2 dice is not 6. So we want the probability of not 6. Well, that's the same thing as 1 minus the probability of getting a 6. So let's look at rolling 2 dice at the same time. Let's think for a moment, how many different outcomes can we have if we roll the dice 6 times, or roll 2 dice? You have 36 outcomes. For the first dice, you could get a 1, 2, 3, 4, 5, or 6. For the second die, you could get a 1, 2, 3, 4, 5, or 6. And then what we're going to do is we're going to write the sums in our table here, since that's what we're interested in. So if I roll a 1 and a 1, the sum is 2. If I roll a 1 and a 2, the sum is 3. If I roll a 1 and a 3, the sum is 4. And you guys get the idea from here, I hope. Okay. So what I need then is the probability of getting a 6. So we need to count up as the number of ways to get a 6. So I count 1, 2, 3, 4, 5 ways of getting a 6. Or of the sum being a 6. 1 minus 5 out of 36. So that gives me 31 out of 36. Okay. The next one is find the probability the sum is less than or equal to 9. So that would be a sum of 2, 3, 4, 5, 6, 7, 8, or 9. That's a lot of things to count. The alternative is to do a complement. So we want not less than or equal to 9. Well, not less than or equal to 9 is the same thing as greater than or equal to 10, right? Oops, sorry. 1 minus not. Oh, I'm sorry. Okay. All right, let me rewrite this. I'm doing a butchering of a job. So we want the probability that we are less than or equal to 9. That was going to be a lot of addition. We can do 1 minus the probability that we're not less than or equal to 9. Not less than or equal to 9 is the same thing as greater than or equal to 10. Right? So what are the things that are not less than or equal to 10? Or, I'm sorry, the things that are not less than or equal to 9? They're 10, 11, and 12. So this is going to be the probability of 10, the probability of 11, and the probability of 12. Why are they minus the whole way? Because that was a minus. Okay. So the probability of getting a 10. 3 ways of doing that. 4 and 11, 2 ways, and 1 way for 12. So when I do that, I get 1 minus 3/36 minus 2/36 minus 1/36, which gives us 30/36. I made a common denominator with the 1, and I reduced that down to 5/6. Okay, so that's all there is to this section. It should have been a quickie. You should have everything you need to be able to do the homework for lecture 4. Now, good luck.